Welcome to video 2 for our lecture video series for Friday, March 24th, where we begin to discuss what's known as a complete ionic equation. So let's start with a definition of what a complete ionic equation is. A complete ionic equation is an expression of an aqueous reaction where all soluble compounds are shown in their dissociated form. So for example, thinking about what we were looking at in our prior example with potassium phosphate, if I were to dissolve 1 unit of potassium phosphate into solution, I would create 3 potassium ions and 1 phosphate ion in solution. And this is what I would use to show in my chemical equation or my expression of the chemical reaction. So for example, let's go ahead and look at the complete ionic equations for the example above. So we had potassium phosphate, of which there were 2, reacting with magnesium chloride, of which there were 3, to form 6 potassium chlorides, of which there were 6, and then we had our magnesium phosphate, Mg3PO4 precipitate, which is in its solid form. It is an insoluble product, meaning it cannot be shown dissociated into its ions. So if I were to write the complete ionic equation, I need to have my correct ionic charges and my correct quantities. So this is going to be very similar to what we did when we made our in-beaker view of this reaction. We're now just going to write it out as a chemical equation. So when I dissolve 2 units of potassium phosphate here, I'm going to create 6, 2 times 3 is 6 potassium ions and 2 phosphate ions in solution. So this comes from my balanced molecular equation. Let's do our other reactant, magnesium chloride. So when I dissolve 3 units of magnesium chloride, I generate 3 magnesium cations into solution, and then 3 times 2 is 6 chloride anions into solution. And scooching this over just a little bit. Let's now look at our products. So we do have an aqueous product here, that is our potassium chloride. So we are going to have 6 potassium cations in the beaker once our reaction is complete, and 6 chloride anions. And then because this is our precipitate, meaning it is not soluble in water, this is going to remain undissociated as magnesium phosphate solid. So plus, that's a highlighter, plus magnesium phosphate solid. This here is the complete ionic equation. This shows everything reacting in this chemical reaction in the actual phase in which they're reacting, meaning are they in solution as an aqueous ion or not, and also in the correct proportion or number or quantity that they're made. So let's do another example. Let's look at the reaction of, let's see here. Let's do ammonium chloride reacting with silver nitrate. Okay, let's think about what ions are going to be generated in solution from each of our reactants. This is the ammonium cation paired with the chloride anion. And for our other reactant, we have the silver cation and the nitrate polyatomic anion. Undergoing our double displacement, where our anions are displacing one another and associate with the other cations. I am going to create, let's look at our compounds here. I've got NH4 plus ion that's going to be associated with my my nitrate ion. And since these have the same charge magnitudes but opposite sign, meaning I have a positive charge and a negative charge, when I build my compound, these are going to come together in a 1-to-1 form to form ammonium nitrate, whose phase I don't yet know because I have not used my solubility rules. All right, now let's look at silver, which has a +1 charge, and chlorine, which has a -1 charge. Again, we have a plus and a minus charge that are equal in magnitude, +1 and -1. So when we build a compound containing silver and chloride ions, we are going to do so in a 1-to-1 ratio. So we have AgCl, whose phase is unknown. So I'm going to just rewrite my overall molecular equation, so to make sure that I'm balanced. So ammonium chloride aqueous comes together with aqueous silver nitrate to form ammonium nitrate, whose phase we do not know, and silver chloride, again, whose phase we do not know. Checking for balancing, 1 ammonium on my reactant side, 1 ammonium on my product side, so I am balanced there. 1 chlorine on my reactant side, 1 chlorine on my product side, I am balanced in chloride. 1 silver on my reactant side, 1 silver on my product side, I am balanced in silver. And then 1 nitrate polyatomic ion on my reactant side, 1 nitrate polyatomic product on my product side. Looks like we're all balanced. So now it is time for us to reference our solubility rules so we can identify which of our products, if either, are an insoluble solid precipitate. So let's see here. I've got ammonium, which is one of our universally soluble cations, regardless of what its anion is. So this means that our ammonium nitrate must be aqueous. It is soluble. And then I have also now my chloride compound. So let's look at our rule for chlorides. All chlorides are soluble except those with silver, which we have here. So silver chloride is not soluble, meaning it will precipitate out of solution as a solid, or it cannot dissolve into its respective ions. So there's no ionic dissociation for our silver chloride solid because it is not soluble. All right, I am now going to come down here and write our complete ionic equation. CIE, complete ionic equation. So to do that, I need to look at the number and charges of all of my ions. And the nice thing about writing complete ionic equations is if you follow my method of determining your product, like if you don't try to do your double displacement in your head, you should already have all of your aqueous species separated out into their respective ions in the correct proportions. So my complete ionic equation is going to contain my ammonium ion, because it comes from a soluble compound that dissociates into its ions. I'm also going to have the chloride ion that is reacting with a mixture of our silver ion and our nitrate ion to ultimately form aqueous ammonium nitrate. So we have ammonium ion and the nitrate ion. And then we also have our undissociated, because it is insoluble, precipitate solid product, silver chloride. So this is our complete ionic equation. All aqueous species were shown in their fully dissociated form, and anything that was not soluble or not in solution was left in its molecular form. So this is our complete ionic equation, and this is what you will do anytime you need to write a complete ionic equation for any other aqueous reaction coming up in the future. So anything that's aqueous will be split up into its respective ions when we write complete ionic equations. Coming up next, we have another way of writing a chemical equation for what happens in an aqueous reaction. That is known as the net ionic equation, which is very similar to the complete ionic equation with just a minor difference. So I will see you in our next video where we discuss net ionic equations.